Every year, more than 10 billion rounds of ammunition are manufactured around the world. That's over 1,000 bullets produced every single second. But how does a lump of raw metal become a precision-engineered projectile capable of hitting a target hundreds of meters away?
Today, we're inside the process that turns lead, copper, and chemistry. That millimeter-level precision is a far cry from where it all began. It started in 9th century China, with the invention of gunpowder, a discovery that would go on to revolutionize warfare and give birth to firearms. For centuries, bullets were nothing more than simple lead balls, hand-cast and dropped into muskets and cannons. Today, that crude craft has become high-precision engineering, where every projectile is a small aerodynamic marvel. So let's see exactly how raw metal becomes high-tech ammunition.
Before we get into how they're made, it's worth understanding just how many types exist. Calibers range from small rounds used for target practice and hunting, all the way up to large rifle cartridges built for long-range precision shooting. Some bullets have hollow tips, designed to expand on impact, commonly used in hunting. And self-defense ammunition, where stopping power matters more than penetration. Others are fully jacketed, built to hold their shape and penetrate deeper. The standard choice for military and law enforcement training. And for the most demanding applications, armor-piercing rounds are engineered with hardened cores, capable of defeating protective plating. Every one of these variations starts from the same basic manufacturing process, just with different materials and finishing steps depending on the intended use. Every bullet begins as a careful selection of raw materials, primarily lead, copper, and for certain specialized rounds, steel or tungsten. Lead is chosen for the core because of its density and malleability, heavy enough to carry momentum, soft enough to deform on impact. Copper, prized for its durability and corrosion resistance, is used to jacket that lead core, helping the bullet penetrate targets while protecting the firearm's barrel from excessive wear. For armor-piercing rounds, harder materials like steel or tungsten take the core's place, giving the projectile the strength to punch through protective barriers. Two more components are just as critical. The propellant, typically nitrocellulose, sometimes combined with nitroglycerin, is chosen for how rapidly it combusts, generating the gas pressure that sends the bullet down the barrel. And the primer, tiny but essential, is made from a chemical mixture sensitive enough to ignite instantly the moment it's struck. Before assembly can begin, each raw material has to become a usable component. Picture molten lead being poured and cast into ingots, then extruded into wire or molded directly into the shapes needed for different bullet types. The copper follows a different path, rolled into thin sheets, then cut and formed into small cups. These become the jackets that wrap around the lead core, adding structural integrity and improving aerodynamics. Even small variations in that copper shell's thickness affect how the bullet penetrates and how accurately it flies. For armor-piercing cores, steel or tungsten is machined with tight tolerances into exact shapes,
capable of defeating hardened targets. Meanwhile, the propellant is produced by chemically treating and stabilizing nitrocellulose,
until it becomes a fine powder that burns fast and consistently. And the primers are made by pressing sensitive chemical compounds into tiny metal cups, ready to be seated into the base of each cartridge. With every component ready, the real assembly begins. First, the lead core is inserted into the copper jacket,
capable of defeating hardened targets. Meanwhile, the propellant is produced by chemically treating and stabilizing nitrocellulose,
a step done with real precision since it directly affects how the bullet behave, both in flight and on impact. Once core and jacket are joined, the bullet is shaped into its final form, some pointed for aerodynamics, others hollow-tipped for controlled expansion. From there, the casing comes into play.
A primer is seated into its base, and a precisely measured amount of propellant powder is loaded inside.
Get this wrong, and the bullet's velocity won't match spec. The finished bullet is then pressed into the primed, powder-filled casing, seated to an exact depth that determines the ammunition's overall length. Finally, the casing is crimped around the bullet, locking it firmly in place so it won't shift during firing. What's remarkable about modern ammunition plants is the sheer speed at which all this happens. High-speed automated lines can produce thousands of rounds per minute, with robotic arms and sensors handling nearly every step. Because these facilities work with explosive materials, they operate under strict safety protocols. Controlled humidity, anti-static flooring, and separated zones for handling propellants and primers.
Despite the speed of production, tolerances are measured in fractions of a millimeter. Quality control never stops.
Every round is checked for consistent weight, dimensions, and appearance. And random samples from each batch are test-fired
to confirm they meet velocity and accuracy standards.
The final stage is packaging, and it matters just as much as everything that came before it. Every bullet that passes inspection is sorted by type and caliber, then carefully boxed with caliber, type, and quantity. Clearly labeled for easy identification. For larger orders, those individual boxes are packed into crates, ready to ship out to retailers, law enforcement agencies, or military units around the world. Each shipment tracked and documented every step of the way. But the story doesn't end once a round is fired. Brass casings, one of the main byproducts left behind on any range or battlefield, are actually among the most recycled metals on the planet, valued almost as highly as the raw copper used to make them in the first place. Once collected, spent casings are cleaned, melted down, and reintroduced into the manufacturing chain, turning what looks like industrial waste into raw material for the very next batch of ammunition, closing the loop on a process that never really stops. And that's how a simple piece of lead and a strip of copper become one of the most precisely manufactured objects in the world. Engineered down to fractions of a millimeter, tested for consistency, and shipped by the billions every single year.
If you enjoyed this episode, drop a like, share it with your friends, and leave a comment telling us where you're watching from.
Subscribe and turn on notifications so you never miss a new upload.
Thanks for watching. We'll see you in the next one.